Following on from some of the early videos, we got to this stage here. Now we need to show that the remainder heads towards zero as n heads towards infinity. We need to show that it works for all values of x. So when x is in the positive realm, we need to show that it works when x is in the negative realm, and when x equals 0. So we need to show the remainder here heads towards 0 as n heads towards infinity. As n heads towards infinity, it means we add this term, we add this term, we add this term. That's what it means when n heads towards infinity. We're adding all these terms. But we also need to show that it works for all values of x. We need to show that it works when x is positive, and when x is negative, and when x equals 0. So the reason why this is difficult, we need to show that this thing here heads towards 0. The reason why it's difficult is because x is moving about, and also n is also moving about. So we need to show that this remainder here heads towards 0. But bear in mind that x is moving about and n is also moving about. So let's look. Three scenarios. The first case 1 is when x is above 0. So case 1 is when x is above 0. Case 2 is when x equals dead on 0, and case 3 is when x is less than 0. So we need to show that it works for all values of x. So let's just look at case 2. It's the easiest one. When x equals 0, so when you put 0 into here, e to the power of 0 will be 1. So this thing here will be 1. When x equals 0, you put 0 into here, this will be 0. Put 0 into here, this will be 0. This will be 0. This will be 0. Or you see, everything will be 0. So 1 here equals 1. So in the case of when x equals 0, the remainder will be 0 because it works perfectly. This is 1 equals 1. So in case 2, when x equals 0, it works perfectly. So it's nice and simple. So now let's look at a case where x is greater than 0. Let's look at a case where x is above 0. So let's look at a case where x is above 0. So we are trying to show that the remainder heads towards 0 as n heads towards infinity for the case when x is above 0. So now let's look at the remainder. So the remainder, let me just rewrite this. So push this out here and then push this up here. So I'm just going to rewrite this as this. Okay, so looking at the remainder. Now let's just look at this bit here. Ignore this for the time being. Remember from the theorem, it says that C must exist somewhere between x and the center. Our center is 0. You don't understand why C must exist. In order for you to do that, you need to understand the proof. But from the theorem, it just says that C must exist somewhere in between x and the center. It must exist somewhere in between the two. At the moment, we don't understand why, so just accept it for the time being. Well, C, e to the power of C must be lower than e to the x, and it must be above 1. So looking at this, we are trying to show, bear with me, we are trying to show that the remainder here tends to 0 as n tends towards infinity. If you look at looking at this bit here must be less than or equal to so forget about this. Just looking at this, e to the power, you see this is e to the power of c. E to the power of c must be in between 1 and e to the power of x. So this thing here, the remainder, our remainder, must be less than or equal to well, if you look at this here, e to the power of x must be greater or equal to e to the power of c, because from the theorem it says that c must exist somewhere in between here. Well, e to the power of c is here. It must be bigger than 1 but less than e to the x. So this must be true. So now take the limits as n heads towards infinity. Remember, we've done this in the past, so I'm asking you to accept this. The limit of this as n heads towards infinity is 0. Remember this. In the in the past, when you see this, I would ask you to imagine it as being a 5. This is like 5 times 5 times 5 times 5 times 5. As n heads towards infinity, it's like so n plus 1 factorial is like 1, 2, 3, 4, 5, 6, 7, 7, 8, and so on. As n gets very big, the denominator here will be a lot bigger than the numerator. I've already explained this many times, so I'm asking you to accept this. So this thing here heads towards 0. So as n heads towards infinity, you can see that this is going to be 0. And don't forget, even though x is moving about, in this case here, it is the n that's moving about here. It is n that's moving about. You can consider this as being like a constant. You can actually take it out here. So this thing here heads towards 0 of this, and then this is a constant. Once I know that x is moving about, but once you've set the problem, this here is now fixed. And once you get to this stage here, it is the n that's moving about. This is fixed. You can, if you want to, take it out here. But the point is that this thing here heads towards well, as n heads towards infinity, the limit of this thing here heads equals 1. So this whole thing here is heading towards 1, towards 0. It's heading towards 0. So this always being bigger or equal to this thing here, this is heading towards 0. So therefore, this must head towards 0 as well. So our remainder actually heads towards 0 here in the case of x being bigger than 0 as n heads towards infinity. So in the next video, we're going to look at a case where x is, in fact, let's do it now. No, I will continue in the next video. Okay.